All right, then let's talk a little bit about the simulation workflows for cable harnesses. So I wanted to use here a little bit simplify scenario, simplify workflows, so we get a better understanding here on that. And let's just assume that we have our data set coming from the 3D Experience platform, and we want to then import it from it to the CST studio. And let's assume here that we have our cable harnesses and corresponding CAD geometry data, which in this case would be the engine bay of the car with the surrounding systems. And in the CST, would like to perform several analyses on this case, and we want to start from the simplest and the shortest simulations, and then proceed to more complex ones, but delivering more sophisticated results, which most likely can confuse a user at the beginning, but because of the simulations and amount of data that provides, user can understand the problems better. And at the end, of course, the result has to be shared back to the, let's call it, single source of truth, basically in our case, the platform, because we want to share this results information with everybody involved with our project. And we want everybody to communicate well and decide what to do with the next steps. So let's move to the import. So I will show you here the video, basically almost in the real time how this procedure starts. So let's assume that we are in the web browser view of the CATIA assembly design on the 3D Experience platform, and here you can see that we are at the stage of really ready to export that CAD data or CAD data set with cables and CAD data to the CST, and this is happening via the Power by connector, which we use. We select the version of the CST that we wanted to run it on the model on, and then the CST will start, and now we can load this data. So we go here in quick form through the credential check, and we are going to be greeted by the window of search, but basically here we can either use the 6W tags or the name of our data set to find it very quickly and check if we have a proper revision of it. So that will going to happen right now. We can preview it and see if this is correct data. So we can interact also with it. And if everything's okay, then we proceed. So now the data is going to be loaded soon to CST. We just need to first create a copy on our local machine of that CST project. And now the downloading data will happen. So depending on the data connection, internet connection, and the data amount, basically this process may vary, time of the loading may vary. So once this is done, then we can see that our data set is present. The cable harnesses, which are created, for example, with CATIA electric design, here are present. They are imported with the corresponding segments, and also it's important that the cable cross sections are also visible and filled. So it simplifies the user experience once setting up and running simulations. One last step is to basically make a link of this local copy to the platform. So this is what you just see. And once everything goes well, basically we'll be greeted by the indicator here, which soon will happen. Yeah. So now, basically, we know that the copy is directly linked to the platform. So now, once we have our results of the simulation, we're able to, with one click of the button, to be honest, send it back to them. All right. So now we are ready to run some simulations. Do I share still the right screen? I apologize. I have clicked the wrong button, of course. All right. So before I proceed to the simulation setup, let's just quickly discuss the setup. As already Andreas mentioned, we have a particular case where we have our main processing unit, let's call it electronic computer unit, which is connected to our digital audio broadcast system with the receiver and the antenna. We have our a front control module, which, for example, can fulfill many functions, but let's concentrate on the fact that, for example, sending the video transmission from the frontal-facing camera via OAVR Ethernet to our main control unit. And this happens via the untwisted or via the twisted pair, shielded or unshielded. And the transmission from the receiver happens via the coaxial cable. And of course, all this particular part has to be supplied with power. And for example, it can be done with 12 volts onboard battery with the setup of the power delivery system, power delivery network, as shown on the picture here. So of course, the CST not only is already user normally see the cable cross section imported from CATIA, for example, from CATIA electric design, but also user has the huge freedom and flexibility to also interact with those wires here and create its own. So for example, I think it's most often case that user wants to play with the shields of the components. And for example, on the cable, once we have a coaxial cable, we can directly interact with its parameters, where we try to create them for you in the way that you can most of them fill up directly from the data sheet of the cable manufacturer. And you can also then in real time basically see how the transfer impedance of this wire is calculated, is good or not. And also now you have multiple options to even create other revisions of that cable, other shields, and see how much they compare to each other. The same stuff, of course, also applies for the twisted pair, where we can not only change the additional location of your inner wires inside twisted pair, you can affect directly its twist information. So is it twisting left, right, and also lay density, but also for creating imperfections, so making the cable more realistic. You can also assign, for example, the offsetting of the wires in terms of the in the center of the wire, and that basically improves the cable realistic view, let's say. And I said at the beginning that the first simulations are quick and fast, quick and short in setup, because they are using Cable Studio Solver, where, to be honest, just in the nutshell here, not going into details, we are using 2D field solver to calculate the field around the cross section, and then with the help from the transmission line theory, we are basically solving those complex wires there. And we are going to engage directly in the first setup of simulations, which is calculating of the, I would say, basic parameters of the wires. First off, which could be calculated by impedance calculator, where we are selecting our given segment. We are assigning particular excitation modes for this cable segment, and we can then, for example, calculate the impedances for coaxial cable, the coax mode and the common mode. This is in reference directly to the 3D reference, which is your CAD model, or you can also, based on this CAD model, you can also specify the simplified platform. And also the differential mode for the twisted pair and the common mode for. Also with the same settings, you can, with the same simulation, you are able to directly get the partial information about the resistance parameter, inductance parameter, and the capacitance parameter of that cable, which is, I think, is very useful if one want to compare in terms or in regards to the data sheet. And relates to the capacitance, it's important to always have the 3D model of the 3D environment around the cables, the cable segments exactly as you wish, or exactly as user wishes. But this is done because we just did that import directly from our CAD software or 3D experience in this case. So once we have this basic parameters checked or verified, now we can move to, I would say, also basic set of the simulation that we have to do to basically see evaluate the performance of these cable harnesses. which let's say it could be the S parameters and the cable crosstalk. So for the S parameters, of course, we can use directly the calculated area impedances. We can feed it to our model, terminate them, to not have any strange surprises. And of course, everybody knows that the basic S parameters, so basically return loss, insertion loss for the twisted pair, on which you can see on the top, for the or the coaxial cable, which is on the bottom. And more interesting results, which in a nutshell, you can say is the what is the coupling level from the differential mode of conversion from the differential mode to the common mode from that or inside that segment. And this is basically delivered to you by the longitudinal, the conversion loss and transfer loss. And if there is any further analysis needed on this particular data set for the Cable Studio, or any other user wants to basically access that, and the data can be exported to it very quickly with the surrogate model, and that can be happen directly from the Cable Studio level or schematic of this Cable Studio project. So from the Cable Studio user, you can export it as the macro model SPICE or the matrices if there is a special need of that. And on the schematic, user can create a touchstone file, or from the touchstone file, there is also a quick ability to rationalize the model with the built-in CST built-in vector fitting, or the more advanced or robust case of the EDM. Okay, cable crosstalk. So cable crosstalk, what we wanted in general speaking do, we want to assign one of the lines as the aggressors and the others as victims, and want to basically see the coupling levels happening in our system. So let's just assume that we wanted to engage typical SMPS device inside the front control module, which then basically spread the noise, as you can see, around the power delivery network. And we wanted to see what is the crosstalk coupling levels to the twisted pair, which is in the close vicinity to it, and also coaxial. You could be used as a for reference case. CST, of course, allows you to define the noise source in many different ways. So you can either go for typical in general and the most quick to set up the absolute worst case scenario, where you just engage the entire system with the broadband, everything broadband noise source in terms of the frequency range. But most of cases basically wanted to assign it directly with the spectrum produced by the DUT, or this basically the culprit in this case. So you can also specify directly from the Design Studio simplified version of the switching noise. You can also use macro for that, which can be found in the ENC workflow button. And there is also possibility to directly import this spectrum as the ASCII file if there is a device running, typical device running. And there is also possibility to attach exactly the circuit in the Design Studio of that given circuitry, and basically generate basically by the simulation, circuit simulation, obtain the signal of it and then feed it here. So I use this in absolute worst case scenario results just for information here and explanation. So we wanted to see what is the crosstalk to the twisted pair, which you can see it's on the top view, on the top graph, and the crosstalk to coaxial cable, which is on the bottom. We try to depict the coupling via the colors. So the black corresponds to common mode, and the blue corresponds to the differential mode. So let's take a look here at the switching example with the switching system, with the switching excitation. We can see that, of course, coaxial cable coupling is much smaller than the twisted pair. This is thanks to the shields of that coaxial cables with the specified profile of the transfer impedance. Of course, the noise will start to rise at beginning frequencies. But what is interesting here, what I already mentioned, is that we can very quickly in CST, and exactly in the same model, we can just very quickly swap the twisted pair with, and swap it with the model where we just add a very simple shield, which could be either based on the transfer on the impedance equation, or could be the compact model of the braid or foil. And we can very quickly check it, how much we can gain, how much we can reduce this crosstalk on that given sample. And you can see that on this graph, we see the previous results, and on the bottom, we see how much it dampens. So if we take a look at the common mode, we see that we have almost 10 times improvement in this case at the fundamental frequency. So once we're done with the, let's say, the quickest simulation, just to see evaluate the cable performance, cable harness performance, we know for sure that the cables are working. They are up to the spec, which to the real samples. And now we can basically proceed to the more complex simulation that we wanted to perform. And let's start from the situation where we wanted to see exactly how this cable harness interact with other systems in our model. And in this case, it's basically how much of this interference coming from PDN can basically upset, can it or can it not upset, for example, our digital audio system. So of course, in order to do that, we need to have not only the cable harnesses, but also the CAD data imported. But you saw that already that it's done. So I just wanted to mention here that in ideal world, the CAD data, which comes from this, mechanical designers, basically, in the ideal world, everything will be perfect. So if the simulation engineer sees this model, he sees that all electrical connections between the parts are done as basically is in reality he expects. He doesn't have to provide any additional changes or make sure that everything is connected. He does not have to remove some very unwanted features, details of that inside that CAD data in order to simplify it and basically run it almost optimally. But this is not the ideal world, and very often happens that this is exactly not the case, and we have to repair it. We have to repair that CAD. And that's why in the 3D Experience platform, we have tools which can help you with this. And we originally started from the tool which is called Power Delta, which has the capability to very quickly delete, not necessarily details, to add the all electrical connection between most important crucial part within this CAD and also the parts that you don't want the connection. Like, for example, one of the most often cases just not having the front bumper, which most likely is plastic, which is connected with the fastener or rivets to the other parts, but basically is not electrical conductive, can happen. And we want to basically make sure that all of these parts are up to the real world. And the Power Data allows you to do all of that. Also can do the checkup, verify this model, and then we're most likely 99.999% sure that once we import it to CST, and we can import it to CST either as the CAD model, either as the mesh model. And then we can run it, and we know for sure that this model will mesh and will run. So in this case, as I said, because we wanted to see the interaction of the model, let's just see the interaction of this PDN coming to that antenna. So this is just for validation purpose here. And in order to do that, we have to run so-called co-simulation, where we are binding together the cable solver with the 3D solver. In this case, it's the TLM solver. So all the information, so the fields generated, results obtained by the cable solver now have to be passed to the 3D mesh, where basically we are getting from that cable voltage and the currents, we are imprinting this to the 3D mesh. So the fields will be imprinted to the 3D mesh around this cable positions. And then the 3D solver takes the job and runs, basically evaluates how the fields basically propagate and how much they interact with other 3D systems. And we are using here TLM solver because we want to run the optimized time domain experience for you. And we wanted to use it with the meshing. Basically here is called octree meshing, where we use the typical scenarios that can help make the mesh replicate make the discretized model represent the 3D better and more optimal. So for example, we use the cell warping to make the mesh more stick to our corresponding body parts, 3D body parts, and we lump the cells in order to save the resources in the sections or in the volumes that basically the solver knows that such a high accuracy is not needed. And just this is basically, I wanted to say this slide is oriented to anybody or any simulation designer who's, for example, waiting still for other engineer or designer to deliver him or her specific model of the antenna, which may happen. And the CST just since the beginning of time, basically the 1D probes, which already were set or presented today many times, which already can get this information about the corresponding field values around the location where the antenna will be. So we can very quickly just position those probes and get the field information. And even so, if we know, for example, know the antenna factor of this, of our antenna, we can also apply antenna factor correction here and get the corresponding voltage at what would be at the antenna terminals later on. But of course, everybody wants to have more accurate models because, I don't know, for convincing reasons. So CST has an option for you, basically it's antenna mega software, which for any antenna enthusiast is a very important and very well appreciated tool because it has such a vast library of antennas which are fully parameterizable, and you can get your model, find your model, slightly tune this model, and then export it to CST as the 3D model, then combine, attach it to your 3D model. In this case, is basically the antenna which you could apply on the windshield. And because it's now the 3D model, we are connecting the 3D port to it. Now we also allow us or create a possibility for us to make this model or receiver band more realistic because we are attaching the matching circuit to it. This can be done with the Design Studio itself or also different software, but then it can be directly imported to the CST. And based on that, we can very nicely recreate the bandwidth of this antenna and our digital audio broadcasting system channels. So once this is done, and once we run the simulation, now the field is coupled and we can read directly what is the power level on our receiver. And we can see by the line, by the blue line that was created here with help from the EMI standard limit lines macro, we can basically very quickly create here the limit line. And based on that, once we are imprinted on the result, we can see that for this particular setup, with this particular cable harnesses setup, we can basically go above the sensitivity levels of that EMI receiver, the DAB receiver, and might also upset it. So there is some, most likely now there are some steps or countermeasures that we apply, for example, filtering or such. And of course, what could it be if the result will be not complete via the 3D field view? And of course, at our particular frequency where the noise is quite big, we can see that it comes directly from the specific resonances of that setup of the cable harnesses. And then at 200 megahertz, where there was a much quiet system, is basically we are out of tune for this harnesses resonances. And okay, that will finish simple setup of this simulation. Let's take a look at the other type of the simulation which we can provide, which you can do for the lower frequency range. And for example, that could be the human exposure simulation. I will use here for this particular model the same cable harnesses as previously, but should also serve its purpose. So in order to run the simulation, we have to run the simulation optimally. We have to choose here the FEM method, and we now have to convert our wires from the cable models to their 3D representation. So you see that the coaxial cables is done as the magenta color, power delivery network as green ones, and the twisted pair is as the blue. Also, the PDN has also the Y split as the 3D model represented here. And the switcher is done directly by use of the Cable Studio functionality, which is called Create 3D Cable. Now we are merging together or marrying together those models. I mean, I'm saying marrying, but we are not relocating the wires to the 3D model because the positioning is already there. So once they're created, they will be at the same position where the cables were, so nothing has to be changed. Cut data, pre-mesh cut data is already present, so we can just hit button of the solver and run it. Sorry. Before we run it, we have to also now allow also the field penetration through the corresponding body parts. And here, because the cables are located beneath the hood and the fender, we have to assign those body parts as, for example, specific thin panel material with the specific material of choice. And once this is done, we can see how the magnetic fields can penetrate. And for that, you can, again, use the 1D probe, magnetic probes. So, for example, two of them are positioned just on top of this the body panel, so fender. And those two probes are located for reference cases in below body panels. So it's just in direct vicinity for those wires. So that's why we have a reference current defined or simulated. And we can see that once the field penetration goes higher, once the frequency go lower here. But of course, we have to complete the picture view based on the 3D fields view, and we can see that with the magnetic field, we can see directly at 100 Hertz where the cables are routed. And if you take a look at the model looking from the front, and we take a cross section, we can also see how levels the penetration of the fields. And we move to 1 megahertz. Of course, this field will no longer penetrate this material. However, we all know that the fields are a very tricky thing because they are always find a way where they can penetrate the model. And in this case, of course, is at this frequency, they are start going through the headlight gasket. Okay, so once we are finished with that, we can now export those results. And let's take a look at the video here. Okay, probably not a mistake again. Let's take a look here at the video. So let's assume that this model that you will see in a second has all these results that you just simulated. And now we just have to do some small steps to make sure that we are exporting the results. So here is, for example, for selecting the 3D fields, we have to, as you see, select the add field probes at the 3D experience tab, and we select which we wanted to import. Also, additionally, we also importing or exporting the data about voltages and currents in time domain, frequency domain from schematic. So once this is done, we just, as I said, we just click this one button and this data will be now uploaded. But we are going to be first greeted by another window where user can validate if this amount of data which was generated, it's enough for its internet bandwidth, and can basically also restrict how much of this data is going to be exported. So let's okay, so exactly here you can see how much of the how much estimated data is there to send, and if there's all of the data needed, then the user can either decide to export it or not. And yes, here you can see those 3D monitors there. And when this is done, now we are switch very quickly to web browser. So this is the stage once you know that the data were successfully uploaded. Okay, yeah. Now we are back in the web browser view. Now we can basically use again the search engine to provide here the CST model name. And once we have it, we can now navigate to the another app, which is Physics Simulation Review app. And here we can basically see all these results that we just exported. So first, we're going to see the preview of the model again. Exactly, and if we press just here this button in a sec, now we have all these results that we wanted. So 1D results, so schematic results, so the voltages, currents, which we can use for further studies, and now the 3D fields, which will be shown right now. Yeah. So here we can see exactly the fields or interact with this model and show the fields which you already saw during the slides. And with that, I thank you very much for your attention here.